Good evening to all of you. Today in our software engineering class, we will be dealing with schedule monitoring and specifically two special methods, that is CPM and PERT. So today's topic will be more on the schedule presentation. We have covered the schedule planning in the previous classes. So we will look into the presentation methods. Then we'll go into the activity network, which is one of the presentations. We'll look into some problems. Then we'll go to the critical path method, CPM, and the PERT methods. So if you have any questions, you keep posting it so that I can keep answering those things. So let's look at how is the project schedule presented. So there are two basic methods, very important methods. One is the timeline chart, which is basically a bar graph. It is also referred to as Gantt chart. So it's a very simple graph in which you draw the timeline. On one side you will have timeline, and on the other hand you will have tasks. And the second one is called the task network or activity network, and it provides an activity flow in the project. So the activities are described in terms of a network. And to identify, so first and foremost, we have to identify the tasks for the schedule. So for identifying the tasks, we will use either a product breakdown structure, which is shortly called PBS, or the work breakdown structure, which is WBS, or a hybrid of these two techniques. So in either of this, what do? We take the product function, which gets related to the process model. We have discussed so many process models. So in one hand we have the product, on one hand we have the process, which is defining all your engineering activities. So these two, we map them, we get it related, and so that the major tasks can be, for the product functionality, can be defined. Then for each major tasks, we will decompose it into lower level tasks. So basically we will get this output from the either by PBS or by hybrid or WBS. The task sets are, it's only a question of which one you take first. In product breakdown, you first take the product, then the task. In the work breakdown, you first take the process or the activities, and then you then you map the product functions to it. So ultimately you get a hybrid method. The task sets are assigned. So you take a set of task sets, because the two small tasks you cannot deal with it properly. So you take a task set, and to the task set you define a related work product and also a milestone. That means when it will be achieved, and so that you can do a scheduling. For effective scheduling, you need these two things. And each task is also allocated the effort and duration. We have done the estimation. So from that estimation, we will get the effort required, the manpower or person hours required, and the duration that it will take, and the interdependency of the tasks. What is interdependency of the tasks? That means two tasks may have some dependency. The dependency can be start to start. That means both are starting at the same time. So to show the dependency of task start to start, you have a task like this, and then you have a task, another task. another task somewhere. So if this is the start, 1 minute. I think I'm getting it wrong. Yeah. So this is the start of task A. This is the start of task B. So if we say that these two are dependent, that means these two must start together. And it is start to start. Finish to finish means only when A will finish, then some other tasks can start. So you will have a relation between these two. This is the node, this is the node. So finish to start. And finish to finish means they must finish together. These two must finish together at the same day. And start to finish, that means when you have one task, this start must be dependent on the finishing of another task. It cannot start unless this is finished. So this is A and this is B. Here this is A and this is B. And let's say this is C. So there can be different types of interdependency between the tasks, how the tasks are related. So that has to be established before we do the schedule network or even the timeline chart. And these tasks will be either represented using the bar graph or the activity chart. We said that the bar graph is also known by the name of Gantt chart. This is a very popular name that is used in all kinds of productions, all kinds of production planning, any engineering activity, not only software engineering. And then you can use tools. There are many tools. MS Project is very popular. Also Primavera is there. And there are some open source tools. If you don't have any tools, you have to use the Excel sheet. But in Excel sheet, you cannot do network. The advantage is that they have a repository of tasks and dependencies. You can give all the data and you can decide which kind of graph you want to do, whether it's activity network or a bar graph. So that is the advantage in this tools, and you can change and you can see so many views. So that is how a project schedule is presented. So you will have something like this, or you will have a network, like any network. We'll see more of it. So let's take this problem. A software product has 3 functional modules. So what we are supposed to do? We are supposed to construct its activity precedence network. Again, we are using a new word called precedence. Why we call it precedence? That means something precedes and something follows. One task will precede another task. That means it comes before it, and this comes after it. So this is the preceding task, and this is the following task. So that's why we say activity precedence network, because it is interrelated. So how we will do? First, we will have to do the WBS, work breakdown structure, or PBS, whatever. But basically, we have to define the tasks. Finally, we have to define the tasks, and also the dependency along it. So let us say this is the table that we have arrived at. So you have a product specification. Task number 1 is product specification. Task number 2, you have module. So because it has got 3 modules, the 3 modules we are denoting it by A, B and C. So we have A here and B and C. Oh, it's moving out. C. And this is B. So we have a product specification, and then you have a detailed module A specification, module B specification, and module C specification. So obviously, the dependency of task 2, 3, and 4 will be task 1. And then you will have a specification review. When you do the specification review, both 2, 3, and 4 should have been completed. So that is why the dependency is on 2, 3, and 4. Then you go to task 6, which is design of module A, then design of module C, design of module C, B and C, then coding and testing of A, B and C. That comes to your activity number 9, 10 and 11. And then finally integration testing. So these will have design module A will have to precede the coding and testing of module A. Similarly, design of module B will precede the coding and testing of module B. So accordingly, an integration test can be done because we are integrating all the modules. This has to be done only after each and every module A, B, C are coded and individually unit tested. So this is your unit test of the module B. So then we will have to draw it. So this is your start button. And from the start button, you come to the activity 1, which is the product specification. From here, you can have 3 parallel tasks. That is the specification of A, specification of module B, specification of module C. Then you have the review. That is the so again these will join in. Then you can again fork into parallel activities. So this is your design, this is your coding, and you have the integration testing here. After the integration testing, you come to the end of the tasks. So this is how a product, a network or a precedence network or an activity network is constructed. One minute. Yeah. So what is network scheduling and monitoring? So how can we use this network scheduling into monitoring? That is the main question. So there are, as we have seen, there are networks. So what we have to now do, we have to take the project network method of representing schedules and see how they can be used in monitoring. So there are 2 monitoring methods. One is the critical path method. So 2 scheduling methods use the project network, which also aid the monitoring tool. So initially we plan it and we create the project network and then we use it for monitoring. So one is the critical path method, which is in short CPM, and then the one which is the PERT. The full form for PERT is program, evaluation and review technique. Both these techniques are driven by information already developed in the project planning activities, because monitoring will always be after the planning. When we do the planning, we start executing. So monitoring comes when we are doing the execution of the project. What has happened? So when we are doing the execution, that time we are getting this monitoring. So we are trying to, what we are monitoring? We are monitoring, that means we are trying to see that the project is going as per the plan or as per the schedule. That is what is the monitoring. So there are 2 methods. One is the critical path method. The other is the PERT method, program evaluation and review technique. And in both the techniques, what is common is that we have to estimate the effort of each task. If it is not done, then we have to break it further. Then we have to be able to decompose the product function and select the appropriate process model and the task set and decomposition of the tasks that we described in the previous slide. Then task, sometimes called the project workdown structure, defines the product as a whole for the individual function. For each individual function, we must have the tasks, the work breakdown structure. So as such, one can have task network for the project from the process model activity, or take the function level decomposition and define the task. So basically this is the same thing that I showed, but it is our answer to what is network and schedule monitoring. Then the interdependency among the tasks are to be defined. And then we can have 2 conventions. One is called the activity on node. The other is called the activity on arrow. So what it means is that in the first one, the activity is here. This is the activity. And this is the precedence. The edges will determine the precedence between two activities. So the activity is on the node. So this is the first act. The other one is that the nodes are just events and your activity is on the arrow. So this is your activity here. And this denotes the start of the activity. This node denotes the end of the activity. So you can put your numbers here, 1 and 2. And this will be your activity A. And another activity can start. This could be your activity B. And this is another node. So this is the start of B and this is the end of B. So this is activity on arrow and this is activity on node, AON and AOA. So there are two different type of this thing. Normally CPM we use activity on our node, and in PERT we use activity on arrow. PERT is a much earlier one, so and CPM is a little later one. How PERT and CPM techniques help the project planning and monitoring? So both are graphical project planning and quantitative monitoring tools, which is not available in the Gantt chart. Okay, and they use the activity network technique. They allow the software planner in the following ways. First of all, it will calculate a boundary time. That means a beginning and an end, a kind of an interval that define a time window for a particular task, and that will provide flexibility for resourcing. That means it will say that if you have an activity A, you can start at a particular time, say T1, and or at T2, to be able to end at a particular time. So this will give a flexibility to you. So that is what is done. And because you have limited resources, so it will be easy for you to, depending on the availability of resources, you can juggle between these activities. So this boundary times is very important, a window. CPM determines the critical path, a chain of critical tasks that will determine the duration of the project. So critical tasks require strict monitoring and for maintaining the schedule. If there is anything wrong in any particular task which is critical, then you will not be able to keep the schedule. So once you have determined the critical path and the critical activities, it is easier for you to put priority to these activities and monitor them. So that is how it helps in monitoring. Then PERT establishes expected time estimates for individual tasks. Expected times, that means it is likely to be in that particular time estimate, and it is a statistical model. So you use the normal variable, standard normal variable method, and you use the time estimate, and it can also predict the probability of completing a task or a milestone in the activity flow network. So you take any particular, you have a big network, you take any particular instance, any node, and you can say what is the probability. If you say that I want to finish it in 60 weeks, then what is the probability of finishing it in 60 weeks? Or if you take the complete completion of if you take the expected value of the time estimate of the full project, then you can say what is the probability that because it's the expected time, so you can say what is the probability that I will finish it in this. Is it 60-70% or is it 80%? How much it is? So you can determine what is the risk in each particular activity or a task. Both PERT and CPM have been implemented in a wide automated tools that we have already seen. So that is one advantage also. Okay. Now let's look at what is critical path method. In the critical path method, you have is the chain of tasks. The critical path is the chain of tasks that determines the duration of the project. So this is one major thing. It also determines the duration of the project. Not only that, it has the chain of tasks which are critical, also it determines the duration of the project. Critical path defines the section of the activity flow which, if disturbed, can delay the whole project. So if any one activity in the critical path is disturbed, then it will delay the whole project. There may be multiple critical paths. This is a question, sometimes it is asked in the short questions. How many critical paths can be there? Is it a single one or it is multiple? You can have multiple critical paths in a project. In a large project which consists of hundreds of tasks, you can have multiple critical paths. Unless all tasks on the critical paths are completed on schedule, the project as a whole will not be able to meet the delivery of the schedule. This is basically the same as this one. The project manager must identify and monitor the critical tasks that lie on the critical path and remove any problem. All hurdles, all risks, all difficulties, constraints has to be removed. Best resources have to be given so that they will not be delayed. But one thing that we have not said here is that when you have multiple critical paths or when you have multiple critical activities on the critical chain, if you make one activity, if you reduce one activity by giving another source, then another non-critical activity may become critical. That means by reducing this, by taking action on a critical path, you may make it non-critical. Something else may become critical. So this is a thing that the project manager has to keep on doing. So if you have a tool, you have a network, one path is critical at one point of time, then you have taken some action. Then after a week or so, after this action has been completed, you find that this has become non-critical, and another path which was non-critical, from non-critical it has moved to critical, and something which is what was critical has moved to non-critical. So that is what is the meaning of critical path method. How to determine the critical path? That is the next question. If I don't ask you, then you should be asking me. To determine the critical path, we have to draw the network, project network, or the activity network, or the precedence network, and we have to do two passes. One is called the forward pass, or the forward direction. We have to traverse the activities in the forward direction, and then we have to do the backward direction. When we do the forward direction, what we have to do is we have to compute the early start and early finish of each task by taking into account the duration and the task dependency. So from the beginning of the project, start of the project, we have to follow the path. If there are multiple paths, each path we will follow up to the end, and we will keep determining for each task this set, start and early finish, early start and early finish. Then we will start from the backward. We will come to the end, and from the end we will work backward to determine late finish and late start. We said no, we will have a window. So this is what we are doing. We are trying to define the window here. The difference between the late finish and early finish, or the late start and the early start, will indicate float and slack. When we do this, we will find that somewhere it is same. These both are same. But many activities it is not same. So we can determine what is the difference. The difference can be a positive quantity or it can be 0. Okay. So if it is 0, then if it is 0 slack, then it is a critical activity. And all the activities which are having 0 slack, they will be on the critical path. So on the total, this path will have no slack. But if you have a positive slack, that means you have a boundary window, you have a leverage. It is a non-critical task. Those are the ones that will provide you the flexibility. So critical path is the sequence of flow of activity where each task is critical. A non-critical path can become critical if the slack time is used up before it starts. So if you have if you have a set of non-critical tasks, A, B, C, D, E, E, and there are a lot of slacks here. But suppose you delay this task or you lengthen this task, you give less resources. So what has happened? The slack is used up. Once the slack is used up, now if you determine your this early start, early finish again, and you will find that B, C, D, E has become critical. So that is how you have to very well use the slack time very intelligently so that you use it so that each task can be completed within the required time. Now let's look at this problem. Determine the critical path in the given network. So you are given a network. Here it is a, what kind of network is this? This is a node, and this is the activity on the arrow. So A is the activity, B is the activity, C is the activity, then E, F, G, H and I. So these are all the activities on the arrow. And what are these? These are events. You can say this is 1, this is 2, this is 3, 4, 5, 6, 7 and 8. 7 and 8. Or you can say this is my end and this is my start. So how many paths are there? There is one path here. There is one path here. And there is one path here. So that's what I have written here. And you can calculate length of each path. So path 1 is you just have to add. These are the durations. These are the duration. Let's say they are months. Okay. So this is 3 months. This is 4 months, 3 months, 2 months. So you can add it. So you will get here 12 months. You will get 13 months and 11 months. So which is the longest? This is the longest. So definitely, because we have said that the critical path is the longest path. So you will get the critical path as the path 2, which is the longest. And it will also determine the duration of the project. So if everything goes well, all tasks are done in the right time, then in 13 months, you can complete this project. Now let's do another one. So you can get a project like, you can get a question like this. You will get a table like this. You have tasks here, A, B, C, D, E, F, G, H. And these are the durations, 30 weeks, 60 weeks, 45, 60, like that. And then you have the precedence. So we are given set of tasks, we are given the duration of each task, and we are given the dependency for what is the precedence activity. So here B and C, for B and C the precedence activity is A. For D the precedence activity is B. Only when B is over, D can start. Only when A is over, B and C will start. Similarly, E will start after B is over. F will start after C is over. G will start after E is over. And H after D, F and G. So what we have to do? We have to draw the CPM network diagram for this data and determine the critical path. So let's do, so basically we have to do what is the procedure that we described earlier. The two paths we have to do, 2 passes we have to do. So for better understanding, I have put the problem here. So here we will do the activity on activity on node diagram, AON diagram, and label each one with this. So we can use the node can be denoted by this. This is a good convention. Here you will have the task name. You can put the duration. So this is given to us, this one and this one. And we have to calculate early start and early finish in the first pass. And in the backward pass, we have to determine what is the late finish and late start. And then we will determine what is the slack. So if we determine that, then the whole activity is determined. So we'll start from here. So initially we will put only the task names and the duration. And depending on the precedence, we will do the activity network. So because B and C can start after A will start, so we will connect these two. Then task D and E will start after B is completed. So these two can start here. And task F depends on C, so it will come here. And task G depends on task E, so it will come here. And task H depends on these 3 tasks, D, F and G. So we will have to connect these 3 together to H. So what we have done here, we have created the activity network using the AON convention. And we have used this AON convention method of denoting the node. And we have put the task labels and the durations in the correct positions. Now we will go to the forward pass. So what you will do, this is the step 2, determine ES and EF. So you will go from left to right, that is the convention. So from task A, because this is 0, so we will start with the 0. That's the convention, that we always start with the 0 day. So because it will take 30, whatever is the unit, it can be days or weeks. So 0 plus 30 will be 30. That means if we start it on 0, then we will complete it on 30. So this is the early start 0 and this is the early finish 30. Now this 30, because it ends in 30, so this can become the early start for task B and task C. So again we will add the durations. So that is what EF is equal to ES plus duration of the task. So we have to add the duration to the early start to get the early finish. So there 30 plus 60 is 90, 30 plus 45 is 75. Again this 75 will go as the early start of here. Now the rule 2 says that ES of task 1 is EF of the preceding task. However, when several tasks converge, for example, D, F and G are converging here. So here you have three things. We have 150 is the early finish of this, and 180 and 90. So which one do you take? Here it is very simple. You just take 90 as 90, 75 as 75. But here you have three. So we need a rule. So what the rule says, that whichever is the higher early start of the next start is the largest of the preceding of the EF times. Because unless this one is over, even if this is over, you cannot start this. So that is why you have to take the highest of 150, 180, 90 to here. So this early start of the task sketch becomes the higher of the early finish of these three tasks, which is 180. Then because this is a zero duration task, that means it's a dummy task. Basically, this is the end task. So this is again 180. Now in the backward pass, you take this 180 to the let finish and go backwards. So that is what we have done here. 180 has come here. Now we have to go backwards. So how we go to backwards? Now we subtract. So what we have to do? We have to do the LF of last task is equal to and last task, and LS is equal to let start is equal to LF minus duration. So we keep reducing. So we take this 180 to here, 180, and then we subtract 30 and get 150 here. Similarly, we take this 180 here. We take the 180 here. We take this 180 to this place. So these three places we have to take the 180. This part I think I have not done it. So 180 we bring here. Since 180 minus 60 is 120. So you get 120 here. And again 150 minus 60 is 90 here. Now here which one will you take? Here last finish. Which one you will take? So rule 2 says LS of the following task. However, LF is equal to LS of the following task. However, when two tasks diverge from a node, that is like D and E from B, then this LF let finish will be the lower of these two. Because if I don't put 90 here, then this cannot start. This may be able to start, but this cannot start. So I have to finish it, let test, I have to finish it by 90 days so that this one can start. So when I come back, I have to use this rule, diverging rule, and take the lower of this into this. Again 90 minus 60, this will be 30, and this will come to 30 here. And here 180, so this will be 180 minus 15. So how much it is? You can determine that. I think 165, and this will be 165 minus 45. So you can determine what is this. So in this I have already completed everything. This will be 180. Just typing mistake here. Yeah, right. So now what we will do, the next third step 4 last is to determine the slack or float. So we will use this formula and determine the slack. When you determine the slack, you will find, see if you mark it, these two are same. These two are same. So this is a critical task. Whereas if you take task F, if you take the task F, if you find that there is a difference between the LFEF and the LSES. So if you subtract these two, you will get. So this task F is non-critical. Similarly, task C is non-critical, and task D is also non-critical. But if you take this path A, B, E, G, H, you will find that each of these tasks A, B, E, G, H, you will find that there is this difference is always 0. So this slack is always 0 in each one. Whereas here it is positive, 180 minus 90. So here you have a 90 or 165 minus this. So you have a very large slack here. Okay. So check it. If there is a mistake, you have to check it. Now the critical path gives the longest path duration. So now if a question asks you what is the duration, so you can add this 30 plus 60 plus 60 plus 30. This is the end task. So if you add this, you will get something like 180, whatever is the unit weeks, whatever is the given in the unit in the problem. So now we have identified everything in the critical path method. Now let's compare and contrast CPM and PERT method. This may be a question for you. So in that case, we have to basically show what is the similarity and what are the differences. So in PERT method, in CPM we had only one duration. For one task, we estimated one duration. That is what we have learned in our estimation classes. But again, we have said that you can also have 3 estimates: optimistic, most likely, and pessimistic values. So in PERT method, we don't consider one single one, but we always consider three durations. And when you have 3 durations, you can say I can create a probability distribution over it. So that is the advantage. And then you can calculate the expected value, and we have used these formulas in our estimation classes. So you can determine the expected duration of the effort, and also you can determine the standard deviation. That means what is the likelihood of it being having a variation. Standard deviation always gives you the variation around the expected value. So expected value is the mean, and this gives you the variation. Pessimistic minus optimistic, this should be this way, divided by 6. The task network is created as in the CPM. So the task network in CPM and PERT are not different, they are same. Only difference is in CPM you have got a single value duration for each, and here you have 3 values. So you have to determine the expected, and you take that expected value and draw the network as you have drawn in the CPM method. And the critical path also you can determine in the same way. You can draw this, or sometimes they denote it like this. I am not going into the details of it. So this is the node, and you can denote your activity on the node, or you can denote it as the event. That means as the start or the end of the event. So you can have an activity here and another activity here. So you can determine the critical path either by using this or that box method that we did. You can determine what we saw in the previous slide. So the critical path duration of the project can be determined as in the CPM. So you can draw that path. Now what you can use the standard deviation. This will give the degree of uncertainty of a task because it's a variation. It's a variation around the mean, the standard deviation. So what it will give? It will give the uncertainty. So if the variation is high, that means it is a very risky task. So you can determine which in the schedule which task is very high risk from the deviations. So that is one of the advantages in the PERT. And then you can convert it into Z value. That means normalized duration. So what you can do, you can convert it into, since you have taken this, you can subtract the mean and convert it into a zero mean variable. Then you can get the Z value, that is called a Z value, that means zero mean value. and then this becomes 0 instead of, so each task you convert like that, each one, then you get a set of z value, so each duration becomes z value. Then there are z tables, there are normal variable tables, so you can use those tables to determine the likelihood percentage for completion date of a task. So that will provide you a predictability. That means you can predict what is the percentage of completing within a particular time. So suppose you get it 40, you get a particular node, suppose this particular node, it says you arrive it at 40 weeks. Okay, then you can say, you can take this 40 and say that what is the percentage I will get finish. By taking the expected value here and by taking the expected value of all the previous nodes, suppose you get that this node you are arriving at 40 weeks, then suppose you convert all this expected value to z value, that means zero mean normalized values by substitution, then you can provide, there are some standard tables, and in that table some graph is there, so you can look it up and you can say this is my probability. For a z value you will get a probability. So that is what I have written here. One can also determine a likelihood percentage of completion date of a task, providing predictability for project. You can do it for any activity, for any task. So all that you have to do is you have to go to that end of the task, that node, and look it up into this table after converting it into z value. So let's take up a problem for the PERT. How the problem? Normally you don't get such difficult problems. Normally you get little simpler problems in the exam because it's a little difficult to provide you all those graphs and everything. So draw the PERT network for the below data and determine the task with maximum risk of schedule deviation. So tasks are given. Again, we will have to give the data have to give you 3 values: optimistic, most likely, due. So what is this? This is the duration or the effort. Duration for the task, or you can say the effort for the task. It is not the duration of the project. The project will depend on so many other things, the dependency and everything. So these are the tasks. Here we have 5 tasks, A, B, C, D, E, and this is the precedence task, the dependency. This is the thing. So now what we have to do, we have to extend this table. So we have to take the most likely, which is the expected value. Oh, sorry, this should have been the expected value, because most likely is coming here. So this is what you have done in the estimation: optimistic, most likely, and pessimistic. And then you determine the expected value by using the formula. This plus 4 times of this plus this divided by 6. And then you determine the standard deviation for each task. That is 12 pessimistic minus optimistic divided by 6. So you can get this. And then you can see that they are quite different. So here it is 1, here it is 0.67, here it is 1.17, here it is 1. So which is the highest? If you look at this, this is the highest. So you can say that B is my most risky task. Here I have got a risky for schedule. I have a schedule risk for B. This can deviate. There is a chance of this deviating because the optimistic and pessimistic values are quite far. The next one you can say this 101.17. Again here you can see there is a large deviation. So by computing this, if you have a tool, you can put all these values. You can immediately see which is the highest, which is the next, which is the next. So you can determine, so this is number 1, this is your number 2 risk, and then this can be your number 3 risk. So like that you can determine, and this will help you in monitoring. And also you can determine the PERT chart. So depict proper dependency. You can you see what we have done. We have used the AOA. You can see we have used the AOA because we have put this. What is this? This is the duration. I have not knowingly I have not put the schedule variation because schedule variation determination again you'll have to add it you have to square it, add it, and divide it. So it is not so simple. So I'm just making the problem very simple. So this has been added, task D and E. So let me go to that. So B depends on A, so it comes here. Then C depends on B, so it comes here. D does not depend on anything. A and D don't depend on anything. So you can put it in parallel paths. But your E will depend on C and D. So to denote this, we have put a dummy activity here so that we can create a new node here, new event. This is the event which denotes the end of task C as well as task D. And from there, the task E will start. So normally in AOA, many times you will find that you will need a dummy activity. What is a dummy activity? You add some new activity which has no duration. It has no effort. It is a zero duration. It's a dummy act just to be able to create a node to show the proper dependency. And this is because it is different from these stars, it is not given by a dash tag. Okay. So ABC, so now that is what depict properly dependency dummy activity has been added between D and E depicted by dashed lines. ABC is critical path and the project duration is expected to be 38.67. Here we are not telling deterministic because PERT is a probabilistic method. So we are adding this is the expected duration, this is the expected duration, this is the expected duration and this expected duration. So 6 plus 7 plus 15.67 plus 10 will add up to 38.67. You can verify this. And if you go by this way, then this is 17 plus 6. So there are two paths. This path is 17 plus 6, which is 23. And this path is more. So obviously, the bigger path, longer path becomes the critical path. So you can determine the critical path by using the PERT method also. And to determine the probability of completing the project in 38.67 weeks, one is to convert to Z value. So each of these duration by taking its the standard deviation and the mean, we have to convert it into standard normal variable with zero mean and then look up in the standard normal variate table. I hope this is clear to you. Does any of you have any specific questions? Okay, I don't see anything. Just one person says, how am I? I'm fine. I hope all of you are doing well. And I hope all of you are enjoying this class. And I'm sure all of you have gone through the main lectures, not just attending this. And this is the summary. So we have gone through the Gantt chart and the activity network. And we have shown that there are two ways of graphical presentation. And we have used the activity or the task network to depict the flow of tasks. So we have taken some problem here. We have used the precedence relation to create the activity network and how the task will flow. Then we have gone into monitoring, how to monitor the project. So for monitoring the project, we have looked into the two methods, CPM and PERT. We determined the methods, how to do it. And we have compared them. We have done some projects on it. 1 minute, please. And we have determined the critical path, we have determined the critical tasks, we have understood how it is used in the predict, in the monitoring. Then we have gone to the PERT method and we have shown the variations associated with the activity duration, and we have done this. And we have also checked the tools that are used, which is a great help in planning and monitoring. See, one thing you must remember is that planning is not done once. It is done initially once, but as and when you execute, when you are monitoring, so what you do, you replan, because things keep changing. You have to take into account all the constraint that comes, all the risks that happen, and so the execution will never happen according to the plan. So you have something called as a plan, and then you have something else which is execution. This is done before you start the project, and this is during the execution, something else will happen. So that is why that is the need of this monitoring. So when you monitor, you find the deviations. When you find the deviations, you have to change the plan. So this planning and monitoring go hand in hand. And that is why you need tools like CPM and PERT, which are both planning tools as well as monitoring tools. And you need tool support for it. Unless you have a tool support, you can't do it, because you have to do it on the fly in the project. So that is what I was trying to explain to you in this doubt clearing session. So I hope you have understood everything. Session. So I hope you have understood everything. In the next lesson, we will be looking into some of the cost monitoring methods. So today we have looked into the schedule, and in the next one we will look into the cost. In the next lesson, we will be So we have seen the planning, we have seen the estimation, we have completed today the schedule monitoring. The next class we will do some cost monitoring, and subsequent classes we will also go into the risk monitoring and some of the quality assurance testing, how to choose the best test cases, and how to determine how many test cases should be there, how to monitor testing. So many of the execution monitoring which is very important in a software project. We will deal with it in the subsequent 2-3 lectures. So nice to have all of you with me. I would have loved that it would be more interactive, like the Zoom or something, but we are working on the YouTube. So my only way is that you post some questions here, which I can see. I don't see anybody. I'm only seeing 2 people having logged in. No questions. So if you don't have any questions, we will end the lesson here, and we will meet again next week. Thank you all.